So recall when you have an n by n matrix A, suppose it has eigenvalues lambda 1 through lambda n. And if lambda 1 through lambda n are distinct, then something nice happens. When they're distinct, that means that A can be diagonalized. You can find a basis so that A has this matrix, the lambdas on the diagonal. Or another way to say it is there's a matrix S such that S inverse AS is equal to this. And we say that A is diagonalizable. Okay. Now, this is really sort of the nicest thing that can happen. This is the simplest and best situation when the matrix is diagonalizable. So today, what I'm going to talk about is what if that's not the case? How can this go wrong? And when it does go wrong, what's the best you can do? What can you replace this with? So let's start with the diagonalizable case. So we've seen that when the eigenvalues are distinct, then the matrix is diagonalizable. Now, oftentimes people ask, is it if and only if? So that is to say, if it's diagonalizable, does that mean that the eigenvalues are distinct? And let's think about that. So the question is, does diagonalizable mean that the eigenvalues are distinct? Well, here's an example. Take A to be a 2 by 2 matrix, and suppose it just has a single repeated eigenvalue, say 3. So that is to say 3 is a repeated root. Is A diagonalizable? Well, since the eigenvalues are distinct, you can't conclude that from this. Maybe, maybe not. The answer is maybe, maybe not. So it's obvious if you just write down 2 examples. This matrix right here is diagonalizable. Obviously, it's diagonal. So just because it has repeated eigenvalues doesn't mean there's anything wrong with it. It could still be diagonalizable. But this matrix here, sadly enough, is not diagonalizable. So this is sort of the key example. This is an example with a repeated root, 3, and it's not diagonalizable. In both cases, the characteristic equation is just 3 minus lambda squared. So you can't tell the difference between these 2 matrices just by looking at the characteristic equation. There's something more that you need to know to determine what the situation is. Okay, so recall we had the notion of complete eigenvalue. And that is to say, we say an eigenvalue is complete if the dimension of the lambda eigenspace is as big as it can be. That is to say, the dimension of the lambda eigenspace is the same as the multiplicity of that eigenvalue. And complete is good. Complete's sort of the nicest situation. So for example, in this case, the multiplicity of the eigenvalue is 2, and the dimension of the 3 eigenspace is 2. And this is complete. On the other hand, in this defective, so to speak, example, the multiplicity is still 2, but the dimension of the 3 eigenspace in this example is what? Well, let's see. You take this matrix 3 minus lambda, you set lambda is equal to 3, and the question is, what's the dimension of the kernel of this? And the dimension of the kernel is 2 minus the rank, and the rank is 1, and so the dimension of the kernel of this is 1. And that's the problem. So this is not complete. That's what distinguishes these two cases, and the way you tell them apart is by looking at the dimension of the eigenspace, or equivalently the dimension of the kernel, after you've subtracted lambda from the diagonal. All right, so let's look at another example. Suppose I gave you a 3 by 3 matrix, and all I told you was that the determinant of A minus lambda I was lambda minus 2 times lambda minus 3 squared. So it has two eigenvalues, one with multiplicity 1 and one with multiplicity 2. So the eigenvalues are 2, 3, and 3. Well, one possibility is it could be diagonalizable, like this. That's the nicest situation. But what else could happen? Well, there's nothing wrong with the 2. Nothing can go wrong there. But because of this repeated 3 here, you could have a block matrix, and it could look like this. The 2 is just the 2. There's nothing to do there. But this little 2 by 2 matrix could look like the one in the previous example. It could have a 1 in the upper right-hand corner. So that's sort of the basic kind of example. You break this thing into blocks, and on each block you can have, if it's not just a 1 by 1 block, there are some further choices. So the dimension of the 3 eigenspace in this example is only 1, not 2. Okay, let's look at another example. Let's suppose you had a 3 by 3 matrix like this, and I asked you if it's diagonalizable, and if it's not diagonalizable, what's the next best thing? So is it diagonalizable, and what are its eigenvalues, and so on. So you compute determinant of A minus lambda times the identity, and I'll spare you the details, but it turns out to be, come out to be the following. Minus lambda cubed plus 7 lambda squared minus 16 lambda plus 12, and I'll also spare you the effort to factor this. It turns out that it has eigenvalue 2 repeated and an eigenvalue 3 with multiplicity 1. So the eigenvalues are 2, 2, and 3. So can you diagonalize this? Well, the 3 has multiplicity 1, so there's no problem there. The question is the 2 eigenspace. And I need to know, is the dimension of the 2 eigenspace 2, as big as it could be, or not? And, well, let's check. If you take A minus 2I, what you get is this minus 3, 4, 9, 6 minus 15, minus 4, 4, and 10. And the question is, what's the rank of this matrix? Well, the last 2 rows are multiples of each other. So you can kill off the last row. And so what you come down to is what's the rank of this matrix. And these 2 rows are not multiples of each other, so the rank of this matrix is 2. Therefore, the dimension of the kernel is 3 minus 2, which is 1. And since the multiplicity of this eigenvalue was 2, that's not as big as it could be. So this eigenvalue is not complete. And so the matrix is not diagonalizable. And because of this 2, we have one of these little 2 by 2 matrices in it with the 1 in the upper right-hand corner. So that is to say, it turns out that you can find a matrix S such that S inverse AS is of this form. this block decomposition is showing you that there's a problem in the 2 with the 2 eigenvector. And for the record, the matrix S, which does this, turns out to be this right here. All right, so that's all sort of an introduction to a Jordan form. This is an example of what I've just been illustrating is some examples of Jordan form. And the basic question in Jordan form is the following. Suppose you have an n by n matrix. And what can you say about an n by n matrix which only has one eigenvalue? It has one repeated eigenvalue, one eigenvalue of multiplicity n. So that is to say that the determinant of A minus lambda I is lambda minus a single number, A, to the n. And, well, again, it could be diagonalizable, but we've seen in these examples that it's not necessarily. And the question is, what are all of the possibilities? So we've seen that it could be this. But if you think about it for a second, it's another possibility is it could be just anything upper triangular with A's on the diagonal. Any matrix like this has this characteristic polynomial. And what does the stuff in the upper triangular part do? When you try and diagonalize it, you may or may not succeed. So possibility, for example, would be a 2 by 2 matrix like this. This is the thing I've been talking about. Or for a bigger example, what about a 3 by 3 matrix like this with 2 1s on the super diagonal? So that's basically what happens in Jordan form. And here's the basic case of Jordan form. It says the following. Suppose A is an n by n matrix, and the determinant of A minus lambda I is A minus lambda to the n. There's one repeated root with multiplicity n. Then you can find a basis. There's a you can find a matrix S, a change of basis matrix S, so that S inverse AS, after a change of basis, is of the following form. Well, it's only A's down the diagonal, and entirely zeros below the diagonal. And above the diagonal, you can put a 1 in each spot just above the diagonal, or a 0, and everything above that is 0. So I'll circle these. I decided to put a 1 here, and a 0 here, and some zeros there, and a 1 down here. On the super diagonal, I can put either 1s or 0s. So that is to say it has A on the diagonals, 0 below, 1 or 0 in each super diagonal. That's the key thing. The super diagonal is the diagonal just above the diagonal. And then everything above that is 0. So it turns out, that's a theorem, that you can always find a basis which puts the matrix into this form. So let's do an example. Suppose I gave you a matrix and I told you that its characteristic polynomial was 2 minus lambda to the 4th. So that is to say it's a 4 by 4 matrix, and it only has a single eigenvalue 2. And after changing basis, I can write A in the following form. Well, let's see. It could be diagonalizable. So I'll put in lots of zeros there. What's another possibility? Well, it has some 2's. So here I've put all zeros down the super diagonal. Another possibility is to put a single 1 up here. So let's do that. 1 and then zeros. Or another possibility would be you could put the 1 right here. Or you could put a single 1 down in the third place. Okay, and let's see, what else? I could put in 2 1s. I could put in, so I'm going to write 4 more matrices here with 2's on the diagonal and see about distributing these 1s. So if I want to put in 2 1s on the super diagonal, I could put them in the first 2 places, or the first and third place, or the second and third place, or I could put in 3 1s. So there are 8 possibilities. Now, it turns out that they're not all really different, but never mind that for the moment. That's clearly all of the possibilities. And one of the questions is, how do you tell which it is? If I give you this matrix and I say that its characteristic polynomial is that, how do you tell whether it's diagonalizable? And if it's not diagonalizable, which of these things you can change a base, you can convert it to with a change of basis? Well, the main thing is you can look at the kernel, the dimension of the kernel of a minus 2i. And that will tell you mostly which of these situations arises. So let's look at that. Okay, so what I've done is I've subtracted 2 from this matrix and written down the possibilities. So, for example, if it's diagonal, and you get 0. If it had a single 1 on the super diagonal, you'd get this. Or if it had 2 1s, you could get, or 2 possibilities, or 3 1s, you could get this. And in the ranks in these various cases are just the number of 1s, which are 0, 1, 2, and 3. And so you see that you can tell which case you're getting by looking at the rank, except in this case, this third line here, where there are these 2 different possibilities. If the rank is 2, it could be 2 1s which are adjacent, or 2 1s that are skipping a step. And so by looking at the rank, you can mostly tell what case you get, but that's not quite enough information. But it goes a long way. And I should point out also that if you only have 1 1, it doesn't really matter which position it's in. So this is really all of the cases. All right, so here's the definition. A Jordan block is a matrix of the following form. It's lambdas, a single value lambda down the diagonal, and a 1 on every super diagonal position. So they're all 1s just above the diagonal. And a Jordan block is, by definition, just a matrix of this form. And it's called a Jordan block of eigenvalue lambda and size n. So it has n minus 1 1s up on the super diagonal. An important example is a Jordan block of eigenvalue lambda and size 1. That's just a 1 by 1. There are no 1s. It's just a single lambda. And so that's important because there don't have to be any 1s. And what we're going to do is we're going to make block matrices and build them up out of Jordan blocks. So you can take a little 1 by 1 Jordan block, and then you could take, you could take a size 2 Jordan block and put them together sort of in block diagonal form like this. And let's see, let's add two little 1 by 1 Jordan blocks to that. So this is the process that we're going to be doing. We're going to be building up matrices out of Jordan blocks like this. Okay. So here's the big theorem. This is the Jordan form theorem. Suppose you have an n by n complex matrix. I'll come back to that and the reason it has to be complex later. You have an n by n matrix. Then there is a basis such that with respect to that basis, after changing basis, in other words, replacing A with S inverse A times S, you can put it into the following form. It's going to have K Jordan blocks down the diagonal. So each one of these is a Jordan block, and everything else is a 0. So each Ji is a Jordan block matrix. It's a matrix of this form with all ones on the superdiagonal and some lambdas on the diagonal. And any matrix can be put into this form. An important example is the diagonalizable case. The diagonalizable case is exactly the one where all of the Jordan blocks are of size 1. So there are no 1s on the superdiagonal. Okay, so let's look at an example. Suppose I gave you a matrix, and I told you that its characteristic polynomial was, let's say 2 minus lambda to the 4th, 5 minus lambda cubed. So it's a 7 by 7 matrix, and it has eigenvalue 2 of multiplicity 4 and 5 of multiplicity 3. So what are the possibilities for the 2 block? Well, it could be diagonal, or it could have block it could look like this, or another possibility is it could be a 3 by 1 block, and the final possibility is it could be 2 by 2 blocks. That's all of the possibilities. Oh, sorry, one last one where it's all ones, a block of size 4. And when lambda is equal to 5, the 3 possibilities are diagonal, or 2 by 1, or a single block of size 3. And the theorem says that this matrix A, after a change of basis, can be put into a block form with of this type. So an example would be the 2 eigenvalue part might be this, and then the 5 eigenvalue part, say, could be this. And the any matrix can be put into one of these forms. Okay, so let's see. One observation here is that the different eigenvalues are really independent of each other. So you wind up with this block decomposition where you only have to analyze each eigenvalue separately. For example, if you had a matrix which looked like this, then you would know that the first thing you would do is you divide your matrix up into a big bunch of blocks of size 4, 2, and 7. And you know that it's going to be of this form. And then the only question is within each of these blocks, how the ones on the superdiagonal are distributed. In other words, the size of the Jordan blocks within each bigger block. Okay. So a possibility would be if, for example, it turns out that the size of the Jordan blocks was like this, and that would say that you had ones on the superdiagonal in the following places. Okay, well, there's just one last thing I want to talk about here, which is this business about having complex matrices. So, well, obviously real matrices are complex matrices, so why did I say that? Well, just one example illustrates this. Take this matrix here, then, of course, the determinant is this polynomial lambda squared plus 1, and this has the roots I and minus I, and so in order to put this into Jordan form, you have to think of it as a complex matrix, and then you can diagonalize it using complex matrices. So when I said Jordan form holds for complex matrices, of course it applies to a real matrix, but the Jordan form matrix that you get might not be real. That might have complex numbers in it.